We all familiar with contact forces, where two bodies apply forces on each other through direct physical interactions. These forces are self-explanatory and need no further explanation. In the previous video, we learned how to calculate the electrostatic force experienced by two charged particles. Now here's the question. How does one charge push on the other charge when there's nothing in between these charges? This is an example of action at a distance, and it doesn't seem to make any sense. Is there something in between that actually letting the two charges interact with each other? Back in 1830, Michael Faraday came up with an explanation by introducing his idea of electric field. What exactly is an electric field? How this revolutionary idea not only solved the problem of action at a distance, but also made incredible predictions that came out true in later experiments. That's what we're gonna learn today. So, are you ready? So here's the story that Michael Faraday told us. Electric charges create electric fields that permeate through all space around them. And the field is stronger near the charge and it gets weaker and weaker the farther out you go. Let's put another charge in here. Now there is already an electric field at this point that was being created by the first charge. Then that field will exert a force on this one. To sum it up, charges create electric fields all around them, regardless of whether there's other charges nearby or not. Now if any other charges wander into this region, it will experience a force due to the existing field. This is actually a much more powerful way of thinking about electric forces and eliminate the magical idea of action at a distance. Now at this point you are probably scratching your head and wondering if this field we have been talking about is really exist, or we are just making up a story to make ourselves feel better. However, as we progress through this course, we will see that this field theory will make predictions, like the existence of electromagnetic waves that can propagate through empty space at the speed of light. Later, Heinrich Hertz verified this prediction experimentally. Moreover, there's a huge benefit thinking in terms of field rather than forces. It keeps things simple and easy to manipulate. In fact, it makes it so that you don't even have to know about the charge distribution that creating that field at all to figure out what the force is gonna be on any charge in that field. Actually, according to the modern quantum field theory, it is the field itself that is fundamental, while charges are merely vibrations within this electromagnetic field. So now we understand the necessity of the idea of electric field and that it's not same in everywhere. It varies point to point. Now basically we want to answer the following two questions. How can we determine the field strength at a particular point in space? How much force will it exert on other charged particles? Now we're gonna define field strength in such a way that it addresses the above questions. Electric field E at a point in space is defined to be the amount of electric force exerts on a unit charge at that point. If charge Q experiences a force F, then electric field at that point is E is equals to limit Q approaches 0 F divided by Q. Remember, this charge creates the field and it was there before we introduced this charge. Here small q is kind of a measuring instrument and referred to as test charge. And the capital Q that created the field we are interested in is called source charge. Here we restricted test charge to be quite small so that it didn't influence the field to be measured through its own field. Now the second part of our query, if we put a charge Q in some existing electric field E, how much force that charge will experience? This is quite straightforward. After rearranging the previous equation, we get F is equals to Q times E. In summary, if I wish to know what the field intensity is at a point in space, I would just bring my test charge, measure the amount of electric force on that test charge, and then divide it by the amount of test charge. On the other hand, if we want to know the force experienced by charged particle in an electric field, we simply multiply the field intensity by that charge. Consider a charge capital Q located at point P prime with a position vector r prime. Now choose any other point P different than P prime. Let's say its position vector is r. Now we want to figure out how much electric field does charge Q creates at this point. Well, for that, let's bring a test charge small q here. According to Coulomb's law, as we discussed in the previous video, force on this test charge is 1 over 4 pi epsilon naught capital Q small q by modulus of r minus r prime cubed times r minus r prime. Divide this by the test charge small q and we get the electric field at P. Now consider a special case. If the charge q locate at the origin, then r prime is 0, and our previous equation simplified to E of r is equals to 1 over 4 pi epsilon naught q by r squared times r hat. Here r hat is called radial unit vector and points radially outward from the origin. Now this is the equation for determining electric field at a point caused by the source charge Q. What does it depend on? Well, it depends on how strong the source is. More charge means stronger field. It also depends on how far away you from the source. Closer to the source, stronger the field. Finally, its direction varies point to point according to the radial unit vector, but it does not depend on the test charge. Okay, that's all for now. I hope you have learned something new. If so, please give me a thumbs up and share with others. Click the link in the description to download my notes on this topic. Be absolutely sure to hit that subscribe button and the bell icon next to it so you are the first to know when I upload a new video. I would love to hear your thoughts in the comment section. Thanks for watching and I will see you in the next video.